Cartesian coordinate system.
A Cartesian coordinate system is a coordinate system that specifies each point uniquely in a plane by a pair of numerical coordinates, which are the signed distances from the point to two fixed perpendicular directed lines, measured in the same unit of length. Each reference line is called a coordinate axis or just axis of the system, and the point where they meet is its origin, usually at ordered pair. The coordinates can also be defined as the positions of the perpendicular projections of the point onto the two axes, expressed as signed distances from the origin. One can use the same principle to specify the position of any point in three-dimensional space by three Cartesian coordinates, its signed distances to three mutually perpendicular planes, or, equivalently, by its perpendicular projection onto three mutually perpendicular lines. In general, n Cartesian coordinates, an element of real n space, specify the point in an n-dimensional Euclidean space for any dimension n. These coordinates are equal, up to sign, to distances from the point to n mutually perpendicular hyperplanes. The invention of Cartesian coordinates in the 17th century by René Descartes, Latinized name, Cartesius, revolutionized mathematics by providing the first systematic link between Euclidean geometry and algebra. Using the Cartesian coordinate system, geometric shapes, such as curves, can be described by Cartesian equations, algebraic equations involving the coordinates of the points lying on the shape. For example, a circle of radius 2 in a plane may be described as the set of all points whose coordinates x and y satisfy the equation x2 plus y2 equals 4. Cartesian coordinates are the foundation of analytic geometry, and provide enlightening geometric interpretations for many other branches of mathematics, such as linear algebra, complex analysis, differential geometry, multivariate calculus, group theory, and more. A familiar example is the concept of the graph of a function. Cartesian coordinates are also essential tools for most applied disciplines that deal with geometry, including astronomy, physics, engineering, and many more. They are the most common coordinate system used in computer graphics, computer-aided geometric design, and other geometry-related data processing.
History.
The adjective Cartesian refers to the French mathematician and philosopher René Descartes, who used the name Cartesius in Latin. The idea of this system was developed in 1637 in writings by Descartes and independently by Pierre de Fermat, although Fermat also worked in three dimensions, and did not publish the discovery. Both authors used a single axis in their treatments and have a variable length measured in reference to this axis. The concept of using a pair of axes was introduced later, after Descartes' La geometry was translated into Latin in 1649 by Frans van Schooten and his students. These commentators introduced several concepts while trying to clarify the ideas contained in Descartes' work. The development of the Cartesian coordinate system would play an intrinsic role in the development of the calculus by Isaac Newton and Gottfried Wilhelm Leibniz. Nicolas Erasme, a French cleric and friend of the Dauphin, later to become King Charles V, of the 14th century, used constructions similar to Cartesian coordinates well before the time of Descartes and Fermat. Many other coordinate systems have been developed since Descartes, such as the polar coordinates for the plane, and the spherical and cylindrical coordinates for three-dimensional space.
Description. 1 dimension.
Choosing a Cartesian coordinate system for a one-dimensional space, that is, for a straight line, involves choosing a point O of the line, the origin, a unit of length, and an orientation for the line. An orientation chooses which of the two half-lines determined by O is the positive, and which is negative. We then say that the line is oriented, or points from the negative half towards the positive half. Then each point P of the line can be specified by its distance from O, taken with a plus or sign depending on which half-line contains P. A line with a chosen Cartesian system is called a number line. Every real number has a unique location on the line. Conversely, Every point on the line can be interpreted as a number in an ordered continuum such as the real numbers.
2 dimensions.
The modern Cartesian coordinate system in 2 dimensions, also called a rectangular coordinate system, is defined by an ordered pair of perpendicular lines, axes, a single unit of length for both axes, and an orientation for each axis. Early systems allowed oblique axes, that is, axes that did not meet at right angles. The lines are commonly referred to as the x and y axes, where the x-axis is taken to be horizontal and the y-axis is taken to be vertical. The point where the axes meet is taken as the origin for both, thus turning each axis into a number line. For a given point P, a line is drawn through P perpendicular to the x-axis to meet it at x, and second line is drawn through P perpendicular to the y-axis to meet it at y. The coordinates of P are then x and y, interpreted as numbers x and y on the corresponding number lines. The coordinates are written as an ordered pair, x, y. The point where the axes meet is the common origin of the 2 number lines and is simply called the origin. It is often labeled O, and if so then the axes are called ox and oy. A plane with x and y axes defined is often referred to as the Cartesian plane or xy plane. The value of x is called the x-coordinate or abscissa, and the value of y is called the y-coordinate or ordinate. The choices of letters come from the original convention, which is to use the latter part of the alphabet to indicate unknown values. The first part of the alphabet was used to designate known values. In the Cartesian plane, reference is sometimes made to a unit circle or a unit hyperbola.
3 dimensions.
Choosing a Cartesian coordinate system for a 3-dimensional space means choosing an ordered triplet of lines, axes, that are pairwise perpendicular, have a single unit of length for all 3 axes and have an orientation for each axis. As in the 2-dimensional case, each axis becomes a number line. The coordinates of a point P are obtained by drawing a line through P perpendicular to each coordinate axis, and reading the points where these lines meet the axes as 3 numbers of these number lines. Alternatively, the coordinates of a point P can also be taken as the signed distances from P to the 3 planes defined by the 3 axes. If the axes are named x, y, and z, then the x-coordinate is the distance from the plane defined by the y and z axes. The distance is to be taken with the plus or sign, depending on which of the 2 half spaces separated by that plane contains P. The y and z coordinates can be obtained in the same way from the xz and xy planes respectively.
Higher dimensions.
A Euclidean plane with a chosen Cartesian system is called a Cartesian plane. Since Cartesian coordinates are unique and non-ambiguous, the points of a Cartesian plane can be identified with pairs of real numbers. That is with the Cartesian product, where is the set of all reals. In the same way, the points any Euclidean space of dimension n be identified with the tuples, lists, of n real numbers, that is, with the Cartesian product.
Generalizations.
The concept of Cartesian coordinates generalizes to allow axes that are not perpendicular to each other, and/or different units along each axis. In that case, each coordinate is obtained by projecting the point onto one axis along a direction that is parallel to the other axis, or, in general, to the hyperplane defined by all the other axes. In such an oblique coordinate system, the computations of distances and angles must be modified from that in standard Cartesian systems, and many standard formulas, such as the Pythagorean formula for the distance, do not hold.
Notations and conventions.
The Cartesian coordinates of a point are usually written in parentheses and separated by commas, as in 10, 5, or 3, 5, 7. The origin is often labeled with a capital letter O. In analytic geometry, unknown or generic coordinates are often denoted by the letters x and y on the plane, and x, y, and z in 3-dimensional space. This custom comes from a convention of algebra, which use letters near the end of the alphabet for unknown values, such as were the coordinates of points in many geometric problems, and letters near the beginning for given quantities. These conventional names are often used in other domains, such as physics and engineering, although other letters may be used. For example, in a graph showing how a pressure varies with time, the graph coordinates may be denoted t and p. Each axis is usually named after the coordinate which is measured along it. So one says the x-axis, the y-axis, the t-axis, etc. Another common convention for coordinate naming is to use subscripts, as in x1, x2, xn for the n coordinates in an n-dimensional space, especially when n is greater than 3, or not specified. Some authors prefer the numbering xo, x1, xn, 1. These notations are especially advantageous in computer programming. By storing the coordinates of a point as an array, instead of a record, the subscript can serve to index the coordinates. In mathematical illustrations of two-dimensional Cartesian systems, the first coordinate, traditionally called the abscissa, is measured along a horizontal axis, oriented from left to right. The second coordinate, the ordinate, is then measured along a vertical axis, usually oriented from bottom to top. However, computer graphics and image processing often use a coordinate system with the y-axis oriented downwards on the computer display. This convention developed in the 1960s, or earlier, from the way that images were originally stored in display buffers. For three-dimensional systems, a convention is to portray the xy plane horizontally, with the z-axis added to represent height, positive up. Furthermore, there is a convention to orient the x-axis toward the viewer, biased either to the right or left. If a diagram, 3D projection or 2D perspective drawing, showed the x and y-axis horizontally and vertically, respectively, then the z-axis should be shown pointing out of the page towards the viewer or camera. In such a 2D diagram of a 3D coordinate system, the z-axis would appear as a line or ray pointing down and to the left or down and to the right, depending on the presumed viewer or camera perspective. In any diagram or display, the orientation of the three axes, as a whole, is arbitrary. However, the orientation of the axes relative to each other should always comply with the right-hand rule, unless specifically stated otherwise. All laws of physics and math assume this right-handedness, which ensures consistency. For 3D diagrams, the names abscissa and ordinate are rarely used for x and y, respectively. When they are, the z-coordinate is sometimes called the applicate. The words abscissa, ordinate and applicate are sometimes used to refer to coordinate axes rather than the coordinate values.
Quadrants and octants.
The axes of a two-dimensional Cartesian system divide the plane into four infinite regions, called quadrants, each bounded by two half-axes. These are often numbered from first to fourth and denoted by Roman numerals, I, where the signs of the two coordinates are I, plus, 2, plus, 3, and 4, plus. When the axes are drawn according to the mathematical custom, the numbering goes counterclockwise starting from the upper right, northeast quadrant. Similarly, a three-dimensional Cartesian system defines a division of space into 8 regions or octants, according to the signs of the coordinates of the points. The convention used for naming a specific octant is to list its signs, for example, plus or plus. The generalization of the quadrant and octant to arbitrary number of dimensions is the orthant, and a similar naming system applies.
Cartesian formulas for the plane. Distance between 2 points.
The Euclidean distance between 2 points of the plane with Cartesian coordinates and is. This is the Cartesian version of Pythagoras' theorem. In three-dimensional space, the distance between points and is, which can be obtained by 2 consecutive applications of Pythagoras' theorem.
Euclidean transformations.
The Euclidean transformations or Euclidean motions are the bijective mappings of points of the Euclidean plane to themselves which preserve distances between points. There are four types of these mappings, also called isometries: translations, rotations, reflections and glide reflections.
Translation.
Translating a set of points of the plane, preserving the distances and directions between them, is equivalent to adding a fixed pair of numbers, a, b, to the Cartesian coordinates of every point in the set. That is, if the original coordinates of a point are x, y, after the translation they will be.
Rotation.
To rotate a figure counterclockwise around the origin by some angle is equivalent to replacing every point with coordinates x, y, by the point with coordinates x, y, where. Thus,
Reflection.
if x, y, are the Cartesian coordinates of a point, then x, y, are the coordinates of its reflection across the second coordinate axis, the y-axis, as if that line were a mirror. Likewise, x, y, are the coordinates of its reflection across the first coordinate axis, the x-axis. In more generality, reflection across a line through the origin making an angle with the x-axis, is equivalent to replacing every point with coordinates x, y, by the point with coordinates x, y, where. Thus,
Glide reflection.
a glide reflection is the composition of a reflection across a line followed by a translation in the direction of that line. It can be seen that the order of these operations does not matter, the translation can come first, followed by the reflection.
General matrix form of the transformations.
These Euclidean transformations of the plane can all be described in a uniform way by using matrices. The result of applying a Euclidean transformation to a point is given by the formula. Where A is a 2x2 orthogonal matrix and B equals B1, B2, is an arbitrary ordered pair of numbers. That is, where, to be orthogonal, the matrix A must have orthogonal rows with same Euclidean length of 1, that is, and. This is equivalent to saying that A times its transpose must be the identity matrix. If these conditions do not hold, the formula describes a more general affine transformation of the plane provided that the determinant of A is not 0. The formula defines a translation if and only if A is the identity matrix. The transformation is a rotation around some point if and only if A is a rotation matrix, meaning that a reflection or glide reflection is obtained when. Assuming that translation is not used, transformations can be combined by simply multiplying the associated transformation matrices.
Affine transformation.
Another way to represent coordinate transformations in Cartesian coordinates is through affine transformations. In affine transformations, an extra dimension is added and all points are given a value of 1 for this extra dimension. The advantage of doing this is that point translations can be specified in the final column of matrix A. In this way, all of the Euclidean transformations become transactable as matrix point multiplications. The affine transformation is given by using affine transformations. Multiple different Euclidean transformations including translation can be combined by simply multiplying the corresponding matrices.
Scaling.
An example of an affine transformation which is not a Euclidean motion is given by scaling. To make a figure larger or smaller is equivalent to multiplying the Cartesian coordinates of every point by the same positive number m. If x, y, are the coordinates of a point on the original figure, the corresponding point on the scaled figure has coordinates. If m is greater than 1, a figure becomes larger. If m is between 0 and 1, it becomes smaller.
Shearing.
A shearing transformation will push the top of a square sideways to form a parallelogram. Horizontal shearing is defined by. Shearing can also be applied vertically.
Orientation and handedness. In 2 dimensions.
Fixing or choosing the x-axis determines the y-axis up to direction. Namely, the y-axis is necessarily the perpendicular to the x-axis through the point marked 0 on the x-axis. But there is a choice of which of the two half-lines on the perpendicular to designate as positive and which as negative. Each of these two choices determines a different orientation, also called handedness, of the Cartesian plane. The usual way of orienting the axes, with the positive x-axis pointing right and the positive y-axis pointing up, and the x-axis being the first, and the y-axis the second axis, is considered the positive or standard orientation, also called the right-handed orientation. A commonly used mnemonic for defining the positive orientation is the right-hand rule. Placing a somewhat closed right hand on the plane with the thumb pointing up, a fingers point from the x-axis to the y-axis, in a positively oriented coordinate system. The other way of orienting the axis is following the left-hand rule, placing the left hand on the plane with the thumb pointing up. When pointing the thumb away from the origin along an axis towards positive, the curvature of the fingers indicates a positive rotation along that axis. Regardless of the rule used to orient the axis, rotating the coordinate system will preserve the orientation. Switching any two axes will reverse the orientation, but switching both will leave the orientation unchanged.
In 3 dimensions.
Once the x and y axes are specified, they determine the line along which the z-axis should lie, but there are two possible directions on this line. The two possible coordinate systems which result are called right-handed and left-handed. The standard orientation, where the xy plane is horizontal and the z-axis points up, and the x and the y-axis form a positively oriented two-dimensional coordinate system in the xy plane if observed from above the xy plane, is called right-handed or positive. The name derives from the right-hand rule. If the index finger of the right hand is pointed forward, the middle finger bent inward at a right angle to it, and the thumb placed at a right angle to both, the three fingers indicate the relative directions of the x, y, and z-axis in a right-handed system. The thumb indicates the x-axis, the index finger the y-axis and the middle finger the z-axis. Conversely, if the same is done with the left hand, a left-handed system results. Figure 7 depicts a left and a right-handed coordinate system. Because a three-dimensional object is represented on the two-dimensional screen, distortion and ambiguity result. The axis pointing downward, and to the right, is also meant to point towards the observer, whereas the middle axis is meant to point away from the observer. The red circle is parallel to the horizontal xy plane and indicates rotation from the x-axis to the y-axis, in both cases. Hence the red arrow passes in front of the z-axis. Figure 8 is another attempt at depicting a right-handed coordinate system. Again, there is an ambiguity caused by projecting the three-dimensional coordinate system into the plane. Many observers see Figure 8 as flipping in and out between a convex cube and a concave corner. This corresponds to the two possible orientations of the coordinate system. Seeing the figure as convex gives a left-handed coordinate system. Thus the correct way to view Figure 8 is to imagine the x-axis as pointing towards the observer and thus seeing a concave corner.
Representing a vector in the standard basis.
A point in space in a Cartesian coordinate system may also be represented by a position vector, which can be thought of as an arrow pointing from the origin of the coordinate system to the point. If the coordinates represent spatial positions, displacements, it is common to represent the vector from the origin to the point of interest as. In 2 dimensions, the vector from the origin to the point with Cartesian coordinates, x, y, can be written as where, and are unit vectors in the direction of the x-axis and y-axis respectively, generally referred to as the standard basis. In some application areas these may also be referred to as versors. Similarly, in 3 dimensions, the vector from the origin to the point with Cartesian coordinates can be written as where is the unit vector in the direction of the z-axis. There is no natural interpretation of multiplying vectors to obtain another vector that works in all dimensions, However, there is a way to use complex numbers to provide such a multiplication. In a two-dimensional Cartesian plane, identify the point with coordinates x, y, with a complex number z equals x plus I. Here, I is the imaginary unit and is identified with a point with coordinates 0, 1, so it is not the unit vector in the direction of the x-axis. Since the complex numbers can be multiplied giving another complex number, this identification provides a means to multiply vectors. In a three-dimensional Cartesian space, a similar identification can be made with a subset of the quaternions.
Applications.
Cartesian coordinates are an abstraction that have a multitude of possible applications in the real world. However, three constructive steps are involved in superimposing coordinates on a problem application. 1. Units of distance must be decided defining the spatial size represented by the numbers used as coordinates. 2. An origin must be assigned to a specific spatial location or landmark, and 3. The orientation of the axis must be defined using available directional cues for n1 of the n-axis. Consider as an example superimposing 3D Cartesian coordinates over all points on the Earth, that is geospatial 3D. What units make sense? Kilometers are a good choice, since the original definition of the kilometer was geospatial. 10,000 kilometers equaling the surface distance from equator to North Pole. Where to place the origin? Based on symmetry, the gravitational center of the Earth suggests a natural landmark, which can be sensed via satellite orbits. Finally, how to orient x, y and z-axis directions. The axis of Earth's spin provides a natural direction strongly associated with up versus down, so positive z can adopt the direction from geocenter to North Pole. A location on the equator is needed to define the x-axis, and the prime meridian stands out as a reference direction, so the x-axis takes the direction from geocenter out to. Note that with 3 dimensions, and 2 perpendicular axis directions pinned down for x and z, the y-axis is determined by the first 2 choices. In order to obey the right-hand rule, the y-axis must point out from the geocenter to. So what are the geocentric coordinates of the Empire State Building in New York City? Using Earth radius equals 40,000/2p, and transforming from spherical, greater than Cartesian coordinates, you can estimate the geocentric coordinates of the Empire State Building, equals. GPS navigation relies on such geocentric coordinates. In engineering projects, agreement on the definition of coordinates is a crucial foundation. One cannot assume that coordinates come predefined for a novel application, so knowledge of how to erect a coordinate system where there is none is essential to applying René Descartes' ingenious thinking. While spatial apps employ identical units along all axes, in business and scientific apps, each axis may have different units of measurement associated with it, such as kilograms, seconds, pounds, etc. Although 4 and higher dimensional spaces are difficult to visualize, the algebra of Cartesian coordinates can be extended relatively easily to 4 or more variables, so that certain calculations involving many variables can be done. This sort of algebraic extension is what is used to define the geometry of higher dimensional spaces. Conversely, it is often helpful to use the geometry of Cartesian coordinates in 2 or 3 dimensions to visualize algebraic relationships between 2 or 3 of many non-spatial variables. The graph of a functional relation is the set of all points satisfying that functional relation. For a function of one variable, f, the set of all points, x, y, where y equals f, x, is the graph of the function f. For a function g of 2 variables, the set of all points, x, y, z, where z equals g, x, y, is the graph of the function g. A sketch of the graph of such a functional relation would consist of all the salient parts of the functional relation, which would include its relative extrema, its concavity and points of inflection, any points of discontinuity and its end behavior. All of these terms are more fully defined in calculus. Such graphs are useful in calculus to understand the nature and behavior of a functional relation,